Go ahead, Veronica.
Okay, my name is Veronica Bess, and today I'll be discussing elastic foundations, and more specifically, the Winkler model analysis. Okay, the first thing I'm going to basically talk about is the basic concept. And what an elastic foundation is when a beam is resting on some sort of compressible foundation, or like soil, basically. And this compressible foundation causes a distributed reaction form on the beam, and this reaction's intensity is basically proportional to the compressibility of the soil. So basically, as a load is applied to the beam deflects and compresses the soil, and that soil's reaction affects the beam. The first person who really saw this kind of model was a German civil engineer, Emil Winkler. To today, this form of analysis is still kind of considered the classical form of analysis. He assumes that at every point, the reaction force of the foundation is proportional to the deflection from that beam at that point. So in other words, what that's basically saying is the deflection and force causes a linear relationship. And he uses that to form his theorems. He also found that soil can basically be modeled with regards to the Hooke's law. So that's why he models the soil basically as a line of springs. And the spring constant is called the modulus of foundations, or the Winkler's constant. And it's basically equivalent to the soil's pressure. This is kind of a more simplified version of analysis for these kind of problems. And so there's a lot of drawbacks. For one, it assumes that the beam is weightless. It does not account for the separation of the soil from the beam. And intuitively, that's actually a really key point, because as you know, soil can't act with tension. So if the beam deflects and separates from the soil, you really can't analyze that very easily. It's difficult to account for additional boundary conditions, other than it just kind of like laying along the soil. It's difficult to apply multiple types of loads. I did see some examples that did that, but it was really ridiculous. So it's not impossible, but it's just very difficult. It's also difficult to allow for changes in subgrade reaction. So if there's a change in the soil density or anything like that, it's very hard to account for those changes as well. And so here's basically the basic model for his kind of solution method. So these are springs, there's a distributed load applied, and it's basically forming a deflection, the compression of the springs. There are basically two primary modeling approaches, either a semi-infinite beam or an infinite beam. Either of these models, you can analyze point loads, applied moment, or distributed loads. So this is basically what a semi-infinite beam would look like with the loading on the end. And you have a deflection and this curvature. And the beam just goes on forever in that direction. And so this is the basic model for a infinite beam with a load in the center. And so this is deflection, rotation, bending moment, and shear. And it's basically what I'll explain later is you use these boundary conditions at x to solve for constants of integration. But it's really, this visual representation makes it pretty clear. Okay, so now I'm really going to talk about the key equations for analysis and the detailed approach. So basically, this guy right here is the most important equation for this entire process. Key equation. W is deflection, K is the constant, and Q is the reaction force. And if you look at this diagram right here, it kind of shows you how they get this equation. So here's just a simply loaded beam. And this is the KW is basically the curvature of deflection. And this is just like a slice, a controlled slice of the beam with all the reactions on it. And that's how he drove that equation. Basically, this guy over here, beta, is a kind of like a constant variable introduced for solving these kinds of problems. And these guys right here are like symbols for the future equations to make things more easy to write, basically. But you'll use these to solve for a lot of the constants. And also, like once you find one of these, there's a table and you can find all of them, or you can solve for them, either or. Okay, so this is the governing equation, which is basically what we will primarily use when we solve these kinds of equations. It's basically the key equation solved in terms of W. And so all these constant C's are from the integration. And basically how you solve for these C's is you use the boundary conditions to cancel them out and then solve for the rest of them using these equations here. And then so basically once you go through that process, you'll get these equations. So this is just a common table you can find in case you don't want to go through this entire process. So if you know that you're solving a concentrated load at the end of a semi-continuous beam, you can just go straight to this table and use these equations instead of going through the entire deriving process. This is for a moment at the end, in the center, and a moment at the center. Any questions over these equations? Again, it's just basically already solved out for these guys using the earlier equations. Okay, so now I'm going to go over a pretty simple equation, an example. Okay, so in this example we have a semi-infinite steel bar with a modulus of elasticity of 200 kilopascals and a square cross-section of 80 by 80 millimeters, and it rests on a recoil foundation with a modulus K of 0.25 newtons per millimeter squared. A downward force is applied at the end, and it's asking us to find the maximum and minimum deflections in the locations. So for this kind of problem, the very first thing you want to do is just kind of use your given equations and solve for your knowns. So I solve for EI, your K, and your beta. And then from there, like I talked about earlier, you're going to use your boundary conditions to basically cancel out some of the constants. And so we know as x approaches infinity, the deflection approaches 0. So even though this is kind of incorrect, I like to think about it as kind of like a cantilever beam to help understand the end conditions. Because as it goes on forever, the deflection cancels out, etc., and everything equals 0. And then at the point where the load is being applied, we'll have maximum shear and 0 moment. And that's what you see here. And also we know that C1 and C2 must be 0 because in the earlier equation, if those weren't 0, the deflection would infinitely increase instead of decrease. Therefore, we know that these constants have to be 0 in order to solve this equation. And from there, C3 and C4 can be solved because we know the shear at x equals 0, we know the moment at x equals 0. So using those, we found our two constants. Okay, and then obviously the maximum displacement occurs at x equals 0 because that's where the load is being applied. And we just, from the table earlier mentioned, I just drew it right here for this case, the concentrated load at the end. We can just plug in 0 for x and solve for our deflection. Then for the minimum deflection, we know that that's going to be where theta is equal to 0. And so we grab our theta equation. And when we look at this, we know that this term here has to be 0 for theta to be 0. So then we go back to our symbols that we mentioned in the earlier slide and grab A. When we solve for our beta x, we know what beta is, so then we can solve for x. And then using this value of x, we can find all of our other terms. And then we plug those into our deflection equation, and we find the minimum deflection. And here's a diagram. Any questions on this example? Questions overall?